Welcome in this new series of lecture from Halliday Resnik Krane, that is Coulomb 2 Part 5th edition. Here we will discuss first of all MCQ solution, then after this series we will discuss some conceptual questions from the Halliday Resnik Krane, then we will solve the few numerical problems. So here from chapter 25, that is all about electric charge and Coulomb's law, I am sharing few MCQs. Showing not few, all of the MCQs. So let's begin. Question number 1. Electric charges A and B are attracted to each other. Electric charges B and C repel each other. If A and C are held close together, they will attract, repel, not affect each other, or more information required. A and B are attracted, so it means that they are having opposite charge. Now B and C repel each other if B is negatively charged so as the C. That's why they are repelling each other. If A and C are held close together. Now A and C when held together, as A is positive charge and C is negative charge, they will attract. So option A is the correct option. Now the next question is, electric charges A and B are attracted to each other, so it means that they are having oppositely charged, that's why they attract. Electric charges B and C also attract each other. So it means B is negatively charged, so as the C is positively charged, that's why they will attract. If A and C are held together, they will attract, repel, not affect, or more information. Now A and C, when they held together, A and C both are having similar charges, that's why they will repel each other, so option B is the correct option. Next question is question number 3. Electric charges A and B repel each other, so it means that they are having similar charges. I write here as A and B as negative charges, you can also take as positive charges. Electric charges B and C also repel each other if B is negatively charged and C is also repelling each other, so it means that C would also be negatively charged. Now if A and C are held together, then they will attract, repel, not affect each other, or more information. A and C, A is negatively charged, so as C is, that's why they will repel each other, so option B is the correct option. Next question is question number 4. If an object made of substance A rubs another object with a substance B, then A becomes positively charged and B becomes negatively charged. Now here two bodies A and B, they are neutral. After rubbing due to force of friction, are actually transferring towards the body. Let me make one thing clear. These are all electrons that are transferring from one body to the body, not the positive charges always. So when electrons from body A are moving towards the body B and B is become negatively charged, then on A there is deficiency of electrons, so it is become positively charged. And next is, however, an object made of substance A is rubbed against an object made of substance C. Now A and C are rubbing against each other, and then after rubbing, now A is become negatively charged and C is become positively charged. So if we take a look on these, what will happen if an object made of substance B is rubbed against an object made of substance C? Okay, if we take a look at this. In this figure, we have more ability to gain electron as compared to, and in this one, A has more ability to gain electron as compared to C. So it means that we will rub with C, then we have more ability to gain electron as compared to C. So B is rubbed with C, then B will become negatively charged and C will become positively charged. So B becomes negatively charged and C becomes positively charged. Option C is the correct option. Now question number 5. A positively charged rod is held near a ball suspended by an insulating thread. Here is the ball that is suspended by insulating thread. Insulating thread means the charges are not actually allowed in the insulator. While this is made up of a conductor, so its charges are free in the conductor. The ball is seen to swing towards the charge rod. What can be conducted? As a positive charge is held near to this neutral body, then it swings towards the rod. Then what it's actually happening, or what you can conclude from this information. Whenever you just can a positively charged or any kind of charge body towards a neutral charge body, then in this neutral body there is a separation of charges of negatively and positively charged. That's why this positively charged rod and in this object there is a force of attraction. So this is the reason that this neutral ball is actually attracting or swing towards this positive charge. So the option that the ball must have a charge to that of rod, that the ball must have a opposite charge. If it is neutral, then it can also swing towards the rod. So the ball may have been neutral originally, but it become charged when the rod was hitting it. No, it's not become charged. There is separation of charges, but not it's actually charged. Without conduction, or you can use electroscope to charge this object. But here it's not touching the rod, that's why it's neutral. Option C is the ball must be conductor. No, this is not possible. The ball must not be a conductor. It could also be an insulator. The next one is the ball is not positively charged, but it could be neutral. The ball is not positively charged, but it could be neutral. Yes, it could be neutral, and then it could swing towards it. So option D is the correct option. Next question is question number 7. A spherical conducting ball is suspended by an insulating thread. A positive point charge is moved near the ball. The ball will attracted to the point charge and swing towards it. It repels from the point charge and swings away from it, and not be affected by the point charge. Now this is the conducting ball that is suspended by this insulating thread, and a positive point charge is held near this ball. If this positive charge is not the point charge, but having a very heavy charge which might be greater than this point charge, then there is possibility that this ball will swing towards it. Now this conducting sphere is very heavy and massive as compared to this small point positive charge. That's why option C is the correct option, and it will not be affected by the point charge. Next MCQ is MCQ number 8. A 3 microcoulomb point charge Q1 is located at distance d away from a -6 microcoulomb point charge Q2. What is the ratio of F1 to an F1? So now let me make one thing clear to you. If we talk about the force of attraction or either force of repulsion, or we are talking about the forces that Q1 is acting on Q2 or Q2 is acting on Q1, then these forces are basically equal in magnitude, right? And if we're taking the ratio here, the ratio of the magnitude, then it would be equal to 1, as the magnitude of both forces are equal. Next question is question number 9. Two 200-pound lead balls are separated by a distance of 1 meter. Both balls have the same positive charge Q. What charge will produce an electrostatic force between the balls that is of the same order of magnitude as the weight of one ball? So here are a few options, and the option D is the correct option. So here 1 point is equal to 0.45359 kg, and here the mass is 200 pounds. So I just multiply it with 0.45 0.4535, then the mass is 90.71 kg. Here the distance between the two balls is 1 meter, so I write it here. Next is, what charge will produce an electrostatic force between the balls that is of the same magnitude as the weight of the one ball? W is equal to md, then m is 90.71 and g is 93%. So here W is equal to force, that is 889 Newton. Now this force or weight is equal to electrostatic force, that is 8 given Q2 by AC. So I put these values here, and what we get here, a charge of the order of 10 raised to the power -2, that is from the option D. That's mean option D is the correct option. Next question is question number 10. Two identical small conducting spheres are separated by a distance of 1 meter. Two spheres are additionally have the same positive charge, and the force between them is F naught. Half of the charge from one sphere is then moved to the other charge, then the force between the sphere is now. Let the originally the force having K due to over one sphere. As the charges are similar, that's why I haven't write here Q1 and Q2. Both are same or identical, that's why I write here Q2 Q square. So you get F naught is equal to KQ square. If Q1 is equal to Q by 2, now he's saying that the spheres already have same positive charge. Now he is saying that half of the charge on one sphere is then moved to the other. When half charge is moved, the Q2 has become Q plus Q by 2. So this is, if we take LCM, then this is equal to 3Q by 2. So now the force become F is Q by 2 for one charge and 3Q by 2 for the second charge, as from one charge half of the charge was moved and in the next it was added as 3Q by 2 by taking LCM of that. So this is one sphere, the distance remains the same. Now 3KQ square by 4, and what you get 3 by 4 of the original force. So option is 3 by 4 F naught and the option C is the correct option. Here is MCQ number 11. Two identical small conducting spheres are separated by a distance 1 meter. These are basically identical spheres and they are separated by a distance of 1 meter. This distance is 1 meter. The spheres already have equal but opposite charge. So one having plus Q and other is having minus Q charge. Force between them is F naught originally. Half of the charge in one sphere is then moved to the another charge sphere. Then the force between them sphere is now F naught by 4, F naught by 2, 3F naught by 4, 3F naught by 2 and 3F naught. When half of the charge from one sphere moved to the second one, let's suppose from half of the charge from this sphere is actually moving toward this. So now this is become Q by 2 and this is neutralizing and it also becomes Q by 2 as half of the charge becomes neutralized when charge from this moving toward this. So actually what you get now Q by 2 as its leave one of half of charge and this gain half of the charge and become neutralized, so left with half charge. So what you get Q over 4. So that is F naught by 4 from the that's 1/4 of the original force. So option A is the correct option. This is MCQ number 12. A point charge Q was located at distance A from the surface of a sphere of radius 2a. A charge plus Q is distributed uniformly throughout the point of the sphere. The magnitude of the electrostatic force between the point charge Q and the sphere is F, where? Find the answer. We have to find the force between these two spheres. As it is mentioned that this sphere of positive charge plus Q is having a radius of 2a and it is separated from a distance from another charge Q with a distance a. So now we have to tell the force. Coulomb law is only valid to the point charges, so you can remember that. And K is 1/4 by epsilon naught, that is the Coulomb constant. So now here F is between these two charges is K. The one charge is Q and the other charge is small q over the distance between two charges. So we are taking the distance from the center of one charge to the center of the other charge. So here from center to this point, this is the 2a, and from this point to this is a. So a plus 2a, you get 3a whole square, right? 3a whole square. Here it's whole square. So 3 3 is a 9a square. So 9 and 4 is a 36. So option D, E is the correct option in which it's force equal to Q, capital Q over 36 by epsilon naught e square. Next question is 13. A positively charged rod is held near a neutral conducting sphere suspended by an insulating thread. This rod sphere is actually hanging with the thread, that is insulating thread, and this sphere will be unaffected because it's neutral, remain neutral but be repelled from the rod anyway, remain neutral but be attracted to the rod anyway, and require a negatively charged and be repelled from the rod and acquire a negatively charged and be attracted to the rod. When a positively charged rod is held near this wall is initially neutral. So when this rod is held together and held near to it, then there would be the separation of charges between this neutral point. Positively charged will repel due to this one, then move towards the left corner, and the negatively charged will attract it from this positively charged, that's why they will move in the right corner. Now there is the displacement of charges. When positive charge will come near to the neutral sphere, but this is not charging, but it's actually attracting, as the separation here is negative and positive. They will attract each other, so option C is the correct. This solid sphere will remain neutral, but it could be attracted to the north end. Now the last MCQ is MCQ number 14. Objects A and B are three identical insulated spherical conductors. They are originally A and B both have a charge plus 3 millicoulomb and have a charge of minus 6 millicoulomb, right? Both have a charge of plus 3 millicoulomb, A and B. You can see here, I have shown. Then an object C is having minus 6 millicoulomb. Now, object A and C are allowed to touch. When A and C will touch, then minus 3 Coulomb charge will be moved towards this one, neutralize, and it will neutralize the charge A, and here now the C will remain the minus 3 Coulomb charge. Then the object B and C allowed to touch. Now B is plus 3 and C is minus 3. Then plus 3 and minus 3 when they touch each other, then they become neutral. Here, if object A and B are now held near each other, they will have no effect on each other, right? If object A and B are now held near each other after touching and after completing all this phenomena, and then all are neutral, A and B now held together, they will have no effect on each other because they are neutral. If instead A and C are held together, then they also neutral, they have no effect. Remember, I have already told you about the touching of these objects and they are becoming neutral. Before neutral, this charge is actually attracting this one and this charge is also attracting this one, and these two are repelling each other. The question or the options are basically after the touching of these spheres, so they are becoming neutral, they don't have effect on it. Thank you.